Hey everybody, I wanted to welcome you to our virtual class for Thursday the 16th of February. Today I'm going to try and keep it pretty brief, and we'll have some Top Hat questions built in. So remember, you have to answer these questions on Top Hat. They're currently assigned as homework, and as you answer them you'll get credit for attending as well. A copy of this note-taking guide that I'm working on today is posted to eLearning, so if you want to print it out and take notes and follow along, you're welcome to do that. And I think it would be helpful. So we left off in class on Tuesday, which for me is today, on section 5.1, and we were talking about a mean and a standard, oh actually we hadn't talked about a standard deviation yet, but we were talking about the mean of a discrete probability distribution. So for reminder, the formula for a mean for a discrete probability distribution is mu, and it's equal to the sum of x times p of x, and the formula sheet itself has little i's, which means each value of x as you go forward. So we went through a calculation of this, and I'm going to review this calculation as we go through variance and standard deviation. So formulas for variance, and you can take a look at your formula sheet in order to see this formula, but for a discrete distribution, variance is sigma squared because it's considered population. This is all outcomes in an experiment, so we have population values here, and it's equal to the sum of x squared times p of x minus mu squared. So generally speaking, you're asked to calculate the mean before you calculate a variance or a standard deviation, and we use the calculation for the mean in the calculation for the variance and standard deviation. And remember that standard deviation is always the square root of the variance. So standard deviation is sigma, square root of sigma squared, which in this case is the square root. Well, that's an awful summation. Let me make a better one. Is the square root of the summation of x squared times p of x minus mu squared. So that is your formula for your standard deviation. Now I'm using a question that you'll see on Top Hat in order to calculate the mean of a discrete distribution. So this Top Hat question just asks you for the mean part. We're going to go ahead and calculate the standard deviation as well. So if I'm going through and looking at my mean and standard deviation, I'm going to give myself some extra room. I'm using my formula to determine what columns I need. So the mean asks me to find the sum of x times p of x. So I'm going to make a column x times the probability of x, and I'm going to calculate that. So looking at that, 5 times 0.3 gives me 1.5, 6 times 0.2 gives me 1.2, 7 times 0.1, 0.7, and 8 times 0.4 is 3.2. So when I add this up, what I get is the mean. So 1.5, 1.2, 0.7, and 3.2 gives me 6.6 for my mean. And that's the answer for your Top Hat question, is 6.6. Remember, when you're looking at a mean, it should be somewhere in this range. So these numbers go from 5 to 8, 6.6 is reasonable for your mean. Now looking at the variance, if we want to calculate a variance, then I need an extra column. So this one says x squared times p of x. Now I'm going to make that in two columns. The first one x squared, because I don't have an x squared yet, and the second one x squared times p of x. So my x squared column means that I'm taking this first column and squaring it. So 5 squared gives me 25, 6, 36, 49, and 64. So that's just an x squared column. The column I really need for the variance is x squared times p of x. So x squared times p of x I'm taking this column here and multiplying by P of X, the second column. Don't multiply ones next door or you'll get the wrong response. So my first one, for example, would be 25 times 0.3 or 7.5. And then I have 36 times 0.2 gives me 7.2. 49 times 0.1 is 4.9. And 64 times 0.4, 25.6. All right, we're almost there. I need for that variance, I need the sum of this column. So I'm going to add it up, 7.5, 7.2, 4.9, and 25.6. Gives me a sum of 45.2. Now the rest is about plugging it into the formula. So if we're looking for the variance, sigma squared, the variance, it's equal to the sum of this last column we just made minus the sum of the first column squared, first column we made. So 6.6 squared. So 45.2 minus 6.6 squared gives me 1.64 for my variance. Now the standard deviation is what you're actually asked for on your homework assignments for this particular section. And if I'm looking for the standard deviation, I'm going to take the square root of this. So the square root of sigma squared, or the square root of 1.64, which in this case 1.64 gives me 1.28. And there you can see that calculation if it was blocked by my face. Sorry about that. Hopefully it wasn't. Okay. All right, moving on. Today we're going to spend most of our time in section 5.2, which is binomial probability. Binomial probability, I have outlined here for you some of the rules and requirements. It's a specific type of a discrete probability distribution. It has certain rules, and those rules are including that it has a fixed number of n identical trials, so you're doing the same thing over and over and over. Now for each trial there's only two possible outcomes. We call one a success and the other one a failure, so you can either have a success or a failure. Each trial is independent, and remember in statistics, independent means that an outcome of one trial can't affect an outcome of another. And in each trial, the probability of a success is called P. Now P is either given to you in the problem or it's something you already know or something you can calculate. So we'll go over one of each type. In each trial, the probability of failure is equal to Q, and Q is equal to 1 minus P. So we calculate the probability of getting R successes in N trials. So going forward, here's another top hat question. I apologize if it's a little bit fuzzy, it didn't convert well here. So suppose that 9% of the population has blood type B. If we choose 18 people and test the blood type of each, we're interested in the probability that 3 of these people have blood type B. So I wanted to define a success and a failure in this question. Now first, if you ask yourself if this is something that is binomial, binomial means that we have repeated trials. In this case it would be each individual person, and each one's independent. So if one person has blood type B, doesn't have anything to do with whether or not someone else that we've randomly selected has blood type B. So this is something that's binomial. And we have to think about what we have for a success. Now, success is not necessarily positive, but it's the thing we want to calculate the probability of. So this says that we are interested in the probability that 3 of these people have blood type B. So we would consider a success being blood type B. That means that a failure is then the complement of that, so B complement would be not blood type B. So here our next question says, suppose that 99% of the population has blood type B, If we chose 18 people and test the blood type of each, same question, except now we want to know what P and Q are. So P is a success, Q would be considered a failure in probability. Now, I said that P would be either given or something that you can calculate. So this is given in the form of a relative frequency. So here, 9% of the population has blood type B, which means that if the probability of selecting a random person with blood type B would be 9% or 0.09. Looking at that, we have it equal to 0.09. And then Q, remember, is equal to 1 minus P. So 1 minus 0.909 or 0.91. Last part of setting up this experiment, what are N and R? Now when we're dealing with a binomial probability, we have N trials, they're identical, and R is the number of successes. So here I would need N successes, or N trials and R successes. So looking at this, the trials is the number of people that we're asking. So our N should be 18. R is the number of successes, and we're looking for the probability that 3 of them actually have blood type B. Now we're going to go through and calculate this probability. And when you're calculating a binomial probability, you have a formula on your formula sheet. And the formula says that the probability of R successes is equal to the combination of N things taken R at a time times P to the power R times Q to the power N minus R. Similarly, we can write that as the combination of N and R, and I can write it as P to the R times 1 minus P, because that's what Q is, to the N minus R. So if we're looking for the probability that we are actually going to draw 3 people out of 18 that have blood type B, then P we've identified as 0.09. We have identified N as 18. We've identified R as 3. We can calculate Q, or we've already actually done that, or 0.91. So if I'm looking for the probability of 3 successes, then it would be the combination of 18 and 3, which I'm going to get from my calculator, times 0.09 to the 3rd power, times 0.91 to the 18 minus 3 power. So putting this combination in my calculator, I have the combination of 18 and 3. And if you haven't figured out how to get this out of your calculator, make sure you ask Google after you finish watching this. So 816, and then I'm just going to put these in my calculator all at once, but I'm going to simplify a little here. So 0.91 to the 15th. Moving this up so you can see it. Putting this in my calculator, 816 times 0.09 to the 3rd times 0.91 to the 15th gives me 0.14464 decimal places. Alright, coin tosses can also be something that's binomial. If you're flipping a coin over and over and over, then you could have an independent experiment, and this can also follow as binomial. So you toss a coin 11 times, what's the probability that you get exactly 7 heads? So in order to apply the binomial theorem, then we're looking for an N value, an R value, a P value, and a Q value. So N is the easiest one to come up with. Here we have 11. So 11 identical trials. Now the probability of 7 heads is what gives us our R value. Now, P is the probability of a success on a single trial, which means if I were to flip a coin one time, what's the probability of a success? Now, this time, P is something we know. So here, P would be 0.5, and Q, 1 minus P, also 0.5. So if I'm looking for the probability of exactly 7 heads, then I have the combination of 11 things taken 7 at a time, times 0.5 to the 7th, times 0.5 to the 11 minus 7. Combination of 11 and 7 gives me 330 times 0.5 to the 7th times 0.5 to the 4th, and plugging that into my calculator, gives me 0.1611 to 4 decimal places. Now, what's the probability of less than 7 heads? Okay, so this time I'm looking for the probability that x is less than 7. Now, discrete distributions, if you're looking for less than 7, numbers less than 7 would be 6, 5, 4, 3, 2, all the way down to 0. So this would be like the probability of 6 plus the probability of 5 plus the probability of 4 plus all the way down to the probability of 0. You could get 0 heads. Now, if you use the formula for this, that means that you are going to have to calculate this probability each time for each one of those. Personally, that's a whole lot of using this formula in order to get this one probability. So we have what's called the binomial probability table, and I want to introduce that to you. Looks like this. You can find it on e-learning, so if you want to print a copy, you can find a copy on e-learning. I will actually print it out and bring it to class when we come back, so you'll have some copies of the binomial table in here. And if you notice, at the very top of the binomial table is the formula for the binomial, or gives you information about the binomial distribution. Now, if I'm looking for a probability on the binomial table, I'm first going to show you how to find one that we have already found. So we just found the probability of 7 successes, and I'm going to go through that same probability with the table right now. So, looking at the table, the first thing you find on the table is your value of n, your sample size. So it follows down the first column, and this is a 4-page table, so it might not be on the first column. So we're looking for an n value of 11. So here I have an n value of 11. Now the next thing you find is this column called R. Look, 11 is actually split on both pages. So the next thing you find is the column called R, and that's your number of successes. So I'm looking for 7 successes in 11 trials. So I'm in this particular row. And the last part is to find your probability, your p-value. Here we said the probability of a success is 0.5, so here is my 0.5, and then where those two things intersect is my probability value. So if I'm looking for where those two things intersect, here I have the probability of 7 equal to 0.161. Now the probability table will only give you 3 digits, and that's all your homework will need. On the test, I will also ask you for 3 digits so it's consistent. Now if I'm looking for the probability of less than 7, then what I'm doing is I'm adding up the values that are in this same column less than 7. So 0.226, 0.226, 0.161, 0.081, 0.027, 0.005, and 0.000. So that gives me what my probability is altogether. So if I were to add those up, I get 0.226 twice, 0.161, 0.081, 0.027, 0.005, 0.000 gives me a probability of 0.726 altogether. And that is the probability of less than 7 heads. So 0.226, 0.226 again, 0.161, all the way to 0.081, 0.027, and 0.005. Gives us a total value of 0.726. Now your homework actually has the binomial table built in, so you can actually click on a link for the binomial table and see the binomial distribution table to calculate your values. Last question for today. This one I want you to use the binomial table, and it says that sociologists claim that 70% of all fathers of married daughters dislike their son-in-laws. I don't know whether that's not true or not, but for the purposes of this problem, if a group of 12 fathers get together, what is the probability that 5 of them dislike their son-in-laws? So this is binomial distribution or binomial probability because we have independent trials. So we're looking for an n value, an r value, a p value. Now if we're looking at the table, we don't have to worry about q. But if you are using the formula, then you'd have to calculate q as well. So a group of 12 fathers, that means that I have 12 for my n. We're looking for the probability that 5 of them dislike their son-in-laws. And our probability comes from here. So sociologists claim that 70%, or 0.70 for our probability here. So looking at the table, the probability of 5, I'm going to get off of the binomial table, shrinking this down, and looking here, the first thing I'm looking for is a value of 12 here. So let me see if I can, nope. All right, a value of 12, and here I have n value of 12, r value of 5, and I'm going to move over until I have the 0.7 column. So let me line that back up. 12, 5, and going across to 0.7, I'm lining it up with the one below, so 0.7 is right here. And if I look at that, I have 0.029. So 0.029 is the probability that I am looking for here to 3 decimal places. And that's it. You should see a review for test number 2 post here shortly. We will review some of these concepts and review for test number 2 in class on Tuesday, and I hope you have a great weekend.